Welcome back, guys. Today we are going to start talking about this second type of intramolecular bonding, and that is covalent bonding. Remember, we had two types. We had the type that formed ionic bonding, and then what we have is covalent bonding. And covalent bonding is, like I said you earlier, this is my kindergarten one. We're sharing is caring. We're all sticking together. We're working together as a unit. So let's go ahead and investigate this. A covalent bond is a bond formed when electrons are shared between electrons. So unlike ionic bonds where they transfer the electrons from one atom to another, in covalent bonding what they're doing is they're sharing. Okay? And by sharing the electrons, both elements are able to fill their valence shell. So they see the electrons that they're sharing of the other element as part of their own, and the other guy sees the other ones as their own. So they're sharing to fill up that outer bond. Because remember, the goal or the whole reason for bonding is to become more stable, to fill up that outermost valence shells. Now, covalent bonds are formed between nonmetals. Those are going to be elements on the right-hand side of the metalloids, or that stair-step line going through the periodic table. So that both covalent bonds must be on the right-hand side. And all we're going to worry about for right now is binary covalent bonds. So when you look at a compound, you see two elements in there. Look, are they from opposite sides of the periodic table? If they are, they're ionic bonds. If they're from the same side, then they are covalent bonds. So example here, here's chlorine. Chlorine, if we look, it's in column 7A, so that has 7 valence electrons. What happens if it was going to form an ion? It would be a -1. But instead, what chlorine's going to do, it's going to bond with another chlorine, and they end up sharing this middle pair here. So this chlorine gets 2, 4, 6, 8 electrons. It's happy. It's outermost shell. This one has 2, 4, 6, 8. It's happy. It has 8 electrons. So they're sharing, and it's a very relatively strong bond. What we see is, in that last case, the chlorine atoms shared 1 pair of electrons. But they can go ahead and share more than 1 pair. They can share 2 pairs or 3 pairs. And this is what we call multiple bonds. Okay, single bonds where they share 1 pair. If they share 2 pairs of electrons, we call it a double bond. Okay, so there's 4 electrons being involved, or 2 pairs. We can look at it in this example here. If we look first at just between sharing with carbon and oxygen, let's look at oxygen. It's got 2, 4, 6, 8. So the oxygen thinks all these 8 belong to it. Okay. Carbon, on the other hand, if we back up just a second, it's sharing one with hydrogen, so it's got 2, and then 4, 6 here, and then 8. So carbon thinks all 4 of these. Now remember, hydrogen's a weird one. It only has an S shell, so its maximum valence is 2. So it's got 1, 2, 1, 2, and everybody's happy by sharing. Now, if they share 3 pairs or 6 electrons, we call them a triple bond. Okay, so we got 1, 2, 3. So covalent bonds, they share the electrons. They're not transferring them. And they can share either 1 pair or 2 electrons, which is a single bond. They can share 2 pairs or 4 electrons, which is double, or 3 pairs or 6 electrons, and we call it a triple bond. Pretty simple. Now, there's 2 basic types of covalent bonds, and it depends on how well they share those electrons. You know, you can share with somebody, right? Picture you have a cookie, right? You can share it equally, break in half. Each person gets an equal half, or you can give them a little bit and you take most of it. Okay, that's not quite as good sharing. Well, covalent bonds are kind of the same way. The first type is a non-polar covalent, and in a non-polar, this is really nice. These guys equally share the electrons. Okay, so the electrons spend the same amount of time with one atom as they do with the other. So there's an equal sharing of electrons. The other type is what we call a polar covalent. Polar, think of our poles on Earth. We have a north and a south. We have opposites. Well, that happens with bonds as well. But what we see in the polar covalent is that there's an unequal sharing of electrons between the atoms. One of the atoms has a tendency to hog the electrons more often than the other. Okay, so it keeps the electrons over by its side more often. what this does, it creates a partially charged on both sides of them. The side that kind of holds on to electrons has more negative charge, and since the electrons have been dragged over there, the other side is slightly positive. And this is called a dipole. Di meaning two poles. So a slightly positive side and a slightly negative side. Now overall, the molecule is a neutral charge. It doesn't have a charge yet, but because the positive is equal to negative. But the side that hogs the electrons more is going to be negative. The side that gets them pulled away is going to be positive because it doesn't have electrons. This is a really important, especially when we start applying it to biology. Polar and nonpolar plays a big role in a lot of things that are going on in our body right now. So here's an example. First one here is a nonpolar covalent bond. So this is CH4. This is methane. Okay, swamp gas. You may have heard of that. What we see is that between each carbon and hydrogen, they are nicely sharing the electrons. They share them equally. Okay, as opposed to water. Water is a great example of a nonpolar. Oxygen is a lot bigger than hydrogen, so it has a tendency to pull the electrons over this way a lot more. And since it's pulling it over this way, we get a slightly negative charge on the oxygen because it has more oxygen, more of the electrons. And then the hydrogen, it's kind of having its electrons pulling away, so we get a slightly positive charge. Overall, this is a neutral atom, but the oxygen tends to be negative. The hydrogens come slightly positive. This is why water can stick to itself. If you've ever heard of adhesion and cohesion, this has to do with the polar nature of water. So two types of covalent bonds. Nonpolar, they share everything equally, or polar, where one molecule holds on to electrons more than the other molecule. Okay, one thing we got to talk about when we talk about covalent is chemical formulas. We've already defined this earlier, and we said a chemical formula just describes what elements are in a compound and how many of each element is there when we use the subscripts to represent it. Well, what we see is that if a substance exists as a molecule, its formula represents one molecule of the substance. So H2O, that is one water molecule. There's two hydrogen and one oxygen in there. Okay, and what we said, remember, molecules are what we call our generic name for compounds that have covalent bonds, that are formed by covalent bonds. Salts were what we call ionically formed compounds. Molecules are what we call covalent. So a molecular formula then simply represents the number of atoms of each element composing a molecule. This is what we've been calling a chemical formula. Okay. Example: water, H2O, 2 hydrogen, 1 oxygen. Carbon dioxide, 1 carbon, 2 oxygens. Okay. Glucose, this is sugar. This is sugar that's produced as a result of photosynthesis. C6H12O6, 6 carbons, 12 hydrogen, and 6 oxygens. Now, when we were working with ionic formulas or ionic compounds, we wanted to get them down into what we call the smallest whole number ratio, or the empirical formula. This is where if we crisscross them, we're crisscrossing a +2 with a -2, they cancel each other out. Well, with covalent compounds, we'll sometimes do the empirical formula as well. Okay, we always use them with ionic compounds, the salts. We know that already. We can also use them with covalent molecules. The reason is, while some covalent compounds may have different molecular formulas, they're going to have the same empirical formulas. Okay, example of this: Mg2O2. This is going to be our molecular formula. Well, if we want, and this is magnesium oxide, it's going to be ionic, right? So what we have to do then is get rid of these, take them down for ionic. So it's MgO. Let's look at glucose, C6H12O6. Now, if we wanted the empirical formula of that covalent compound, well, we reduce it by the least common factor, which is 6. So we divide everything by 6, so we get C1H2O1. What if we had multiplied by 3? So we had we could have a different substance but have the same empirical formula. So sometimes they'll ask you for empirical formula, other times they'll ask you for molecular. And this will come in later on in the semester or even next semester when we start talking about percent composition. So keep this in mind. Okay, naming covalent molecules are relatively easy. Okay, we don't have to worry about crisscrossing charges. Okay, what we do, we look at the first element, and we use a prefix. That's remember, a word that goes in front of something else if there's more than one atom present. So if it's like C1, we'd write carbon. If it's C2, we'd put a prefix in front of it. Okay? And then the second element, it always gets a prefix to indicate the number of that atom. So here's my suggestion. Let's always go back to two molecules you guys are already familiar with. Carbon dioxide and carbon monoxide. Okay, real simple. Carbon dioxide, this tells me it's one carbon, two oxygens. Okay, carbon monoxide, one carbon, one oxygen. Okay, and then you put an IDE on its end. Okay, carbon dioxide, carbon monoxide. Real simple. But you do need to know the prefixes. And there are, one is mono, two is di, three tri, four tetra. If you ever played the game Tetris, right? Four little boxes on there, think of Tetris. Five is penta, six is hexa, seven is hepta, eight is octa. Okay, you need to memorize these. Okay, you need to have these memorized. I'm not giving these on a test, and these are ones that you currently need to know. So pause this, make sure you get these copied down, because you're going to have to memorize these prefixes. Okay, let's try some examples here. Let's start with the one we already know. Carbon dioxide, CO2. Carbon is only one subscript, so we don't need to put a prefix in front of it. But the second word always gets a prefix and the ending's changed to "ide." How about this one? CCl4. Same thing. Only one of your first element, so it's carbon, and our prefix for 4 is tetra, so carbon tetrachloride. PBr3. Phosphorus tribromide. P2O5. Now in this case we do have more than one, so we're going to have to put our prefix in. So our prefix for 2 is di, so diphosphorus, and we get 5 oxygen, 5 is penta, and then change the ending to ide, so it's diphosphorus pentaoxide. One more, N2O. Okay, well, the first one's got 2, so it's got to be dinitrogen monoxide. Okay, notice we didn't put 2 O's. It wasn't mono and then oxide. We dropped one of the O's here, so it just becomes monoxide. When you have two of the same letters here, drop one of them. Monoxide would sound weird, so it's just monoxide. Okay, so vowel at the end of the mono prefix is dropped when elements begin with the vowel 2. Okay, so monoxide is the big one that we were worried about. Mono and then a vowel starting there. Okay, I want you to write the name for the following molecules. Copy these down, and then pause the video, copy them down, and then come back. We'll check out and see how you did. Oh, one more. Okay, here we go. First one, carbon tetrabromide. Second one, dichlorine heptaoxide. Okay. Now notice it's only the mono that we worried about dropping the letters. Okay, with the 2 letters there. Dinitrogen pentaoxide, boron trichloride, nitrogen monoxide, and then the last one here, see if you're paying attention, magnesium chloride. Well, why am I using prefixes? Because it's an ionic compound. Magnesium is a metal, chloride is a non-metal. Don't forget what you already learned. Okay? That's, as we add more on, you got to remember, you already learned about ionic compounds. Now, the other thing I don't want you to do is to go try to use prefixes with the ionic one. So this shouldn't be magnesium dichloride. No, that's not going to work. Magnesium chloride. Keep them straight. This is where things start getting a little more complicated because you got to keep them separated. Okay. Don't forget what you've already learned. Okay, so let's do it the other way. I'll give you the formula for these next ones, and you see if you can write I'll give you a name, and you see if you can write the chemical formulas. This was the easy way to go. Oops. So go ahead and pause those, write them down, and then come back and let's see how you did. CS2, carbon disulfide. Dinitrogen tetrahydride. Third one, carbon tetrachloride. Hey, we already did that one a little bit ago, so you better got it right. Diphosphorus trioxide. So pretty simple. Once you have the The name going back the other way is pretty simple there. Alright guys, so this is all it is to basic covalent molecules. The first word, you use a prefix with it if your subscript is 2 or greater. Second word always gets a prefix, even if it's 1, and ends with "ide." Pretty simple, but you do need to know those prefixes 1 through 8, so make sure you start learning those now. And please, please, please do not get the rules for ionic bonding, naming of salts, confused with the naming of molecules. That will mess you up. Alright guys, until next class, take care and I'll talk to you soon.